Hello, I am Mrs. Edwards, and today we're going to evaluate all 6 trig functions given a point on the terminal side of an angle. I have here a mnemonic device just to help you remember which quadrant each of the trig functions is positive in. Now, this mnemonic device is used for your main trig functions, sine, cosine, and tangent. As I say the words, all students take calculus, we're going around starting in quadrant 1 and working our way to quadrant 4. So quadrant 1, all, quadrant 2, students, quadrant 3, take, and quadrant 4, calculus. All right, so all there in quadrant 1 is sine, cosine, and tangent are positive in quadrant 1. In quadrant 2, students is for that S for sine. Sine is positive in quadrant 2. T, take, or T, tangent in quadrant 3. So tangent is positive in quadrant 3. And then there in quadrant 4 for calculus, that stands for that C, cosine is positive in quadrant 4. You could, of course, reason this out yourself. You know that all points on the unit circle are cosine comma sine. So if the x-coordinate represents cosine, the only way the x-coordinate is going to be positive is if you move forward to plot a point, which would put you in quadrants 1 or 4. And then if points come in cosine comma sine, sine being that y-coordinate, the only way the y-coordinate is going to be positive is if you graph a point and you plot it up. In other words, that y-coordinate being positive, putting you in quadrants 1 or quadrants 2. But this is just a quick reference, and you actually do know all 6 trig functions. Although this mnemonic device of all students take calculus is really just for those main trig functions, sine, cosine, and tangent, inadvertently you know the other trig functions as well, as long as you know which functions are each of these reciprocal functions. Okay, for example, sine and cosecant are reciprocals, cosine and secant are reciprocals, and tangent and cotangent are reciprocals. So since we know in quadrant 1 that sine, cosine, and tangent are positive, we also know that their reciprocal functions, cosecant, secant, and cotangent, are positive in quadrant 1. In quadrant 2, the sine is positive, and the reciprocal function for sine is cosecant. So we know that cosecant is also positive in quadrant 2. Tangent is positive in quadrant 3, and its reciprocal function is cotangent. That means that cotangent is also positive in quadrant 3. In quadrant 4, cosine is positive, and its reciprocal function is secant. That means that in quadrant 4, secant is also positive. Okay, so let's go ahead and do this one really quick to make sure you understand where things are positive and negative. Notice it says, what is the sign of the 6 trig functions on the interval pi over 2 comma pi? Okay, pi over 2 comma pi, again, that is not a coordinate, that is an interval. So it's saying angle measures just after pi over 2 through pi. Pi over 2 is up here, top where 90 degrees would be, through pi. So this is referring to quadrant 2. You can use an interval to refer to a quadrant rather than saying quadrant 1 or 2 or 3, etc. Okay, so there in quadrant 2, all students take calculus, students standing for S. So here in quadrant 2, the only trig function that is positive would be sine, and then the reciprocal function for sine is cosecant. So in quadrant 2, sine and cosecant are positive. So the answers to those would be positive, making all of the other trig functions in quadrant 2, those ones would have negative answers. Ultimately, knowing the sign of the trig function will help us with the very last step of this problem. So we want to start by plotting the point -5, -2, and then creating an angle where the terminal side goes through this coordinate. Okay, so I'm plotting the point -5, -2, so back 5, down 2. Then to draw in that angle theta, of course, we're going to start the initial side on the positive portion of the x-axis. We're going to rotate counterclockwise, and we're going to rotate, and then the terminal side is going to go through -5, -2. Now this point is not on the unit circle, but it is on a circle. So the next thing that you want to do is to draw a triangle on the bow tie, so when I say draw a triangle on the bow tie, think about like a bow tie. Here is a bow tie, and that just helps you remember where you should draw the triangle. But ultimately, the triangle that you draw, you're just going to simply connect the point directly to the x-axis. So no matter where the coordinate is that you plotted, just draw from that point directly to the x-axis, and you will have created a right triangle that would have been on the bow tie. Okay, now that I have that right triangle, I'm just going to emphasize the side lengths. If I were to plot the point back 5, down 2, the side length here is 2, and the side length over here is 5. As I said, this point is on a circle. It just doesn't happen to be on a unit circle. So this, from the origin out here to the point we plotted, that's the radius of the circle, and we can use the Pythagorean theorem to find that length. So setting that up, 2 squared plus 5 squared equals the radius squared. We end up getting square root of 29 for the radius. All right, now that I have those side lengths, let's go ahead and use what's called the reference angle. And so that reference angle right in there, that positive acute angle, that is the angle that we're going to use to label our sides. So with respect to that reference angle, the 2 would be known as opposite, the 5 would be your adjacent, and then the square root of 29 is your hypotenuse. Now that I've labeled each of these with adjacent, opposite, and hypotenuse, I can start to answer the question, evaluate the 6 trig functions. Now, right now, as we use opposite, adjacent, and hypotenuse to start writing down the answers, we have not yet considered if the answer is going to be positive or negative. We're going to do that last. Okay, but so, ka, toa. Sine is opposite over hypotenuse. So evaluating those, sine is going to be opposite, which is 2 over hypotenuse, which is root 29. I rationalized by multiplying the top and bottom by the square root of 29 for my final answer. Cosine, so ka, adjacent over hypotenuse. Cosine is 5 over root 29. And multiplying by root 29 over root 29, we have our rationalized answer there. Tangent is like slope, the y-coordinate over the x-coordinate. That is also the same thing as TOA, opposite over adjacent. So 2 over 5. After we've got these 3, we just use the reciprocal identities. And so sine and cosecant are reciprocals. So I'm just going to take the answer to sine and flip it over to get the answer to cosecant. So we end up with root 29 over 2. The reciprocal to secant is cosine. So I'm just going to flip over the answer to cosine to get the answer to secant. And lastly, their cotangent's reciprocal is tangent. So if I flip over the answer to tangent, I end up with 5 over 2. All right, we do have the correct ratios, but we need to worry about the sign. Theta is an angle measure that puts us in quadrant 3. So all students take calculus. So in quadrant 3, the only trig function that is positive is tangent, and it's reciprocal, which would be cotangent. So when I finish up these answers, tangent and cotangent are positive, and all of the other ones are negative. Okay, so just notice there, tangent is where it's positive, and so since tangent is positive, all of these other are going to be negative. And notice tangent and cotangent have positive answers, and then the rest of them I made those negative. Okay, so we have our final answer. A quick recap, okay, to this problem so that you don't have to rewatch this all over again. Step 1, plot the point. Then draw a ray that goes from the origin through that side, and then you're going to connect that point directly to the x-axis, which creates a right triangle on the bow tie. After that, you're going to use the coordinate to label the side lengths, distances, so in this case 5 and 2, and then you're going to use the reference angle to decide which one is opposite, adjacent, and hypotenuse. Use the Pythagorean theorem to find the length of the radius. And lastly, go through SOHCAHTOA and the reciprocal functions to figure out the answers to sine, cosine, tangent, cosecant, secant, cotangent. Very last step, just decide, is the sign of the answer for that angle theta, is it positive or negative, using all students take calculus. Most of you will have stopped the video after that last example, but I wanted to review coterminal angles for those of you that needed that quick review, because you will have to do a couple problems on your assignment tonight with the coterminal angles. So a coterminal angle, you can get them by simply adding it or subtracting a complete circle as many times as you want. So in other words, if you're in degrees, you could add 360. You could add 360 twice, add 360 three times. You could subtract 360 once, twice, 3 times. The main thing, oh my gosh, blah, blah, blah. Most of you will have stopped this video after that last example, but for those of you that need a quick review of coterminal angles, I want to run through 2 examples. So coterminal angles, when you start rotating, like in this case, I rotate 30 degrees. If you have another angle that when you rotate it, you end up stopping in the same location, then that would be a coterminal, sharing of the terminal side, coterminal angles. So to get coterminal angles, I can add or subtract 360 degrees as many times as I want. So for example, if I subtracted 360 degrees from 30, I would get negative 330. Graphing negative 330, I would start there at the x-axis and rotate clockwise 330 degrees, but notice we end up in the exact same location. If I add 360 degrees to 30, I get 390. So let's graph 390 degrees. That would require us to do 1 complete circle and a little more. But notice again, all 3 of these angles, the terminal sides are in the same location. There are an infinite number of coterminal angles because I could not just add 360, maybe I go 30 plus 360 plus 360, and I'm going to land in the same location. One of the ways that you use this property, the coterminal angles, is if you want to find the sine of 30, the sine of negative 330, or say the sine of 390. All of these have the same answer. So if you have an angle measure that is really big or really small, to make the problem easier, you could just add or subtract 360 degrees as many times as you want until you get to a smaller angle that is perhaps on the unit circle. So if I wanted to find sine of 390, the first thing I would do is subtract 360, and then I would think sine of 30. Similarly, if I had sine of negative 330, the first thing I would do would be to add 360 to turn that into the sine of 30. Now I could go to my unit circle, and the answer to sine is the y-coordinate, and the y-coordinate at 30 degrees would be root 3 over 2. So all of these have an answer of root 3 over 2. You can do the same thing when it comes to radians. You can add or subtract 2 pi as many times as you want. So for example, if I subtract 2 pi, now granted I would want a common denominator. I would multiply top and bottom by 3, making that minus 6 pi over 3. But pi over 3 minus 6 pi over 3 is negative 5 pi over 3. And if I rotate backwards, 5 pi over 3, so clockwise, 5 pi over 3, I land in the same location. They share the same terminal side. Similarly, if I subtracted 2 pi twice, instead of just once, because you can add or subtract 2 pi as many times as you want. If I subtract 4 pi, I'm going to also get a coterminal angle. Okay, so notice it lands in the same spot. But really, in this particular case, the sine of all three of these end up being the same answer. Sine at pi over 3, the y-coordinate at pi over 3 happens to be root 3 over 2, and so that would be the answer to all of these. But the main takeaway is if I wanted to find the sine of negative 5 pi over 3 or the sine of negative 11 pi over 3, the first thing I would do would be to add 2 pi to negative 5 pi over 3 to turn it into sine of pi over 3. Or if I wanted to find sine of negative 11 pi over 3, I would add 2 pi twice. So I'd add 2 pi and I'd add another 2 pi to get it to look like sine of pi over 3, which makes the problem a bit simpler.